Chapter 14, Quantum Mechanical Postulates. Section 14.2, Quantum Mechanical Postulate 2. Quantum Mechanical Postulate 2 states that for every physical observable, such as position, momentum, or energy, there is a corresponding operator in quantum mechanics. The quantum mechanical operators can be applied to the wave functions of a system, and the quantum mechanical operations can transform those wave functions. Now let's look at several examples. The position of a particle isn't observable. In classical physics, we use x, y, and z to specify the position of a particle in the 3 dimensions. In quantum mechanics, we have corresponding operators, x, y, and z with a caret on top. When you see a caret, it's an operator. We apply those operators to wave functions, and the corresponding operation is multiplied by x, y, or z. For example, if you apply this x operator to sine x, the result is the product of x and sine x. Momentum is another physical observable. In classical mechanics, we have P equals mv, or P sub x equals mv sub x in the x direction. We have similar equations for the momentum in the y direction and z direction. Correspondingly, we have quantum mechanical operators. We put a caret on top of P. Now we have a momentum operator. This P sub x is the operator in the x direction. The corresponding operation is to apply negative I h bar delta over delta x to the wave function. For example, if the wave function is sine x, we just need to apply this to sine x. We will get negative I h bar cosine x. Similarly, we have corresponding momentum operators in the y direction and z direction. H bar is the reduced Planck constant. H bar is simply the Planck constant over 2 pi. We plug in the numbers. H bar is roughly 10 to the power of negative 34 joules second. And this I is the square root of negative 1. I is an imaginary number. Postulate 2 states that for every physical observable in classical mechanics, there's a corresponding quantum mechanical operator. In general, operators transform functions and numbers. Again, there are some more general examples over here. If we apply x operator to psi, it's simply x times psi. We apply y operator to psi, it's just y times psi. Now what if we apply this momentum operator to psi and we get negative I h bar delta over delta x of psi? So we do need to take the first derivative of this wave function with respect to x, and then the result multiplied by negative I h bar. That's the result of applying the momentum operator to psi. And we have x, y, and z directions. We have similar equations. Now for a particle in a one-dimensional world, let's say x direction, we have this simple equation. We'll apply the momentum operator to psi. We get negative I h bar times the first derivative of psi with respect to x. If the wave function does not change with time, then we lose this variable t. There's only one variable in this equation, that's the position. So when we apply this momentum operator to psi, we get negative I h bar times d psi over dx. So we switch the notation from delta to d because in this case we have only one variable. It's single variable calculus here. There are many more observables in physics, like kinetic energy, potential energy, and total energy. In classical mechanics, the kinetic energy of a particle is half mv squared. In quantum mechanics, we have a notation here. We put a caret on top of this E sub kinetic. What's the corresponding operation? Well, it gets more complicated. It's negative h bar squared over 2m. And then we have the sum of 3 second derivative operators. We need to apply all this to a wave function. And really, you take the second derivative of the wave function with respect to x, with respect to y, with respect to z, sum everything up, and then multiply the sum by negative h bar squared over 2m. That's how the operation works. Potential energy. In classical mechanics, we use this notation, E sub potential, or sometimes just PE as potential energy. And the difference between kinetic energy and potential energy is this. Kinetic energy depends on the motion of the particles. Potential energy depends on the position of the particles. In quantum mechanics, we use this notation. We put a caret on top of E sub potential, or simply use V with a caret on top, and the operation is just multiplied by the function of V. V is a function of the position of the particle. What about the total energy? In classical mechanics, it's denoted by E. In quantum mechanics, it's denoted by H with a caret on top. The name is Hamiltonian. The Hamiltonian operator is equal to the kinetic energy operator plus the potential energy operator. So now we have the kinetic energy operator here, we have the potential energy operator here. The sum would be the Hamiltonian. Now, for example, if we apply the Hamiltonian operator to psi, it's equivalent to the sum of applying the kinetic energy operator to psi and then apply the potential energy operator to psi for a 3D particle. For a 3D particle, we have x, y, and z. In this kinetic energy operator, we have x, y, and z in the potential energy operator. Equivalently, we can write this. H psi is equal to negative h bar squared over 2m. Now, inside this parenthesis, we just apply those second derivative operators to psi individually and sum them up. And finally, when we apply the potential energy operator to psi, it's just multiplication. The potential energy operator, V with a caret, being applied to psi is equivalent to a multiplication between the function of the potential energy and psi. Finally, we'll look at angular momentum as a physical observable. It's a three-dimensional vector in the three-dimensional world. There are three components. In classical mechanics, we use L sub x, L sub y, L sub z as the components of the angular momentum in the x, y, and z direction. In quantum mechanics, the notation is similar. We just put a caret on top of Lx, Ly, Lz. But what are the operations? Well, it's negative I h bar times y, delta over delta z minus z, and then delta over delta y. It looks a little strange over here. Why so complicated? Well, just remember, in classical mechanics, we know the angular momentum is this r, the radius vector. The radius vector cross product the momentum vector. So if you know how to deal with the cross product of two vectors, that would be great. But if not, well, the cross product of two vectors can be expressed as a 3x3 determinant. I, j, k are the unit vectors in the x, y, and z direction. X, Y, Z are the three components of the radius vector. Px, Py, Pz are the three components of momentum in the x, y, and z direction. And there's a way to decompose a 3x3 determinant into three 2x2 determinants like this. So you have this I multiplied by this 2x2 determinant here, and then j multiplied by this determinant xz, px, pz. But you also need to remember to put a negative sign here. Now let's look at this k unit vector. It's also multiplied by a 2x2 determinant. Over here, xy on top, px, py on the bottom right here. Now the sign is positive. So we need to have this positive, negative alternatively. If you're doing some, larger determinants. And now we can easily evaluate 2x2 determinants. Over here it's just y times pz minus z times py over here. And now remember, pz has a corresponding quantum mechanical operator. The quantum mechanical operator of pz is negative ih bar delta over delta z. So really you are looking at y times pz here. Now over here, py, what is py in quantum mechanics? It's negative ih bar times delta over delta y. So that's why you see this form as the x component of the angular momentum operator in quantum mechanics. And similarly for L sub y, the corresponding operator can be expressed by using this and then put a caret on top of px and pz. If you put a caret on top of px, it becomes an operator. It's negative ih bar times delta over delta x. And the pz operator is negative ih bar times delta over delta z. Alright, this is just a animation for looking at the angular momentum in classical physics. This L is R cross product P. The expression of angular momentum in classical physics can be expressed as the x component plus the y component plus the z component. I, j, k are the unit factors in the x, y, and z direction. The corresponding angular momentum operator in quantum mechanics can be written similarly. You just don't forget to put a caret on top of the momentum, and we have this expression. The x, y, z components of the angular momentum operators are the three equations. Again, L sub x corresponds to negative ih bar times y delta over delta z minus z delta over delta y operation. So again, this is gonna be an operation, and when we apply the L sub x operator to a function, essentially we are applying this whole thing to that wave function. And L, the three-dimensional vector of angular momentum, is the sum of the three components, in this case the three operators in the x direction, y direction, and z direction. So if you apply this angular momentum vector to a wave function, well, you will end up with a three-dimensional vector. Here we review how to deal with determinants, especially 3x3 determinants. This is a very simple example. If you have a 3x3 determinants, how do we evaluate the value of this? Well, what you want to do is pretty simple. You first write out this determinant, alright, the first column, the second column, the third column, and then you copy the first column here, and then you copy the fourth column here. Alright, so now what you need to do is you need to draw 6 arrows. 3 arrows this direction, 3 arrows the other direction. The 3 blue arrows will be positive. So you're gonna do negative 7 times negative 9 times 2. You get positive 126. And you just multiply these three numbers, negative 140. Multiply these three numbers, 12. And now you need to subtract the three red arrows. Over here, you need to subtract the product of 7, negative 9, and 4. You need to subtract the sum of this. You need to subtract the sum of this. And you can see the blue ones, alright, you do pluses. The red ones, you do minuses. But in this case, the blue ones are negative, so you do minus negative numbers. The result is 324. Here's a numerical example problem 14.2.1. Let's evaluate those determinants. Those are all 3 by 3 determinants. So first one, 1, 2, 3, 4, 5, 6, 7, 8, 9. All you need to do is these three numbers, 1, 5, 9, right? And then 2, 6, imagine a 7 here, so 2, 6, 7. And then 3, 4, 8, because you need to just copy this column and this column here and here. And then you get this. And then you do backward. You do 3, 5, 7. So backward 3, 5, 7. So it's just slash versus backslash. Alright? Slash versus backslash. So you have negative 3, 5, 7. Alright, and then 8, 6. Okay, over here it should be 1. So it's 8, 6, 1. So right here. And then finally 2, 4, 9. And then the result is 0. And this one is actually equivalent to this one, because if you pay attention to all those numbers, I simply rotated those numbers by 90 degrees. When that happens, we're not gonna change the values over here, because you still have 1 times 5 times 9, and you still have 4 times 8 times 3, so like this. You still have 2 times 6, 2 times 7, so like this. Alright, so the same values. Okay, these two same values. Finally, we have some variables in this, but the same principle. If you do not like to copy the first column and second column here and here, there's another way to do it. You just do 1 times 5 times z, so this direction. Remember, we're gonna do this direction from top left to bottom right. Alright, and then 2 times 6. Alright, 2 times 6. And then you need to find another element that's not in the same row or column with this element 2 or this element 6. That's x, so 2 times 6 times x. Alright, and then 4 times y, and then times 3, because this 3 is not in the same row or column with 4 or y, so 3 times 4 times y. Alright, and then we change the direction. 3 times 5 times x, it's gotta be negative. And then 6 times y times 1, it's negative. 2 times 4 times z, it's negative. So we got this expression. Anyway, it's pretty simple to do.